This is a quick lesson to introduce you to relevant prerequisite material and introduce you to the concepts of thermodynamics as we head into the thermodynamics unit. To review heat and temperature, the fundamental principle that we've been looking at throughout this material is conservation of energy. That's true at all times, at all places in the cosmos, and we can take advantage of it. The advantage, the benefit of doing conservation of energy is that it is a state function. We only have to consider the beginning state and the end state, and we don't care how whatever happens in between those two states. We will quantify work and heat from one state to another, but we don't care how work and heat got transferred. It's just a quantity that we will keep track of in conservation of energy. We then moved on to temperature. We will still be looking at temperature. Temperature is a fundamental concept of thermodynamics. There's different scales, and my tip here is if you're not sure what scale to use, check the constants in the equation. If you're working with specific heats, often those are in degrees Celsius, as opposed to the Stefan-Boltzmann constant or the Boltzmann constant, which are in Kelvin. Right after temperature, we went to kinetic theory, where we learned that each molecule in a substance at a temperature is moving at some speed, and we take an average over that whole container, and we get some sort of average speed corresponding to the temperature of that object. There is a more rigorous equation and way to deal with this, but for now, in introductory physics, I am going to focus on a molecule. We don't care what shape it is, and so this mass in here is for the mass of a single molecule. If we want the kinetic energy, if we want the energy of the whole system, the thermal energy of the whole system, we would take this quantity and multiply n number of molecules. We talked about the difference between internal energy and heat, and remember that heat is a quantity of energy in process. Internal energy can be possessed by an object, but heat is in process from one object to another. We looked at types and mechanisms of heat transfer. This may come up, but again, like I said, with state functions, we really don't care how the energy enters or leaves the system. We're just accounting for it. You may see these concepts in conjunction with solving problems in order to incorporate and cohere the material for you across several units. We then focused on consequences of heat flow. The most important and common one being temperature change. And we will see this as we move forward into thermodynamics with state functions. There's an initial temperature and a final temperature and a temperature change. And so we will be using this equation. As we study thermodynamics, we are maintaining a model of a gas, which means that phase change we won't see often, even though thermodynamics applies to all substances everywhere. We're going to focus our model to gases only because it's simple. We can think about the molecules really easy and not worry about different types of energy going on. We can really study the fundamental concepts. And so we won't see phase change very much, though you might conceptually. The last thing I covered was the ideal gas law, and I covered that last so no one would use the ideal gas law equation on fluids and solids. It is one of the fundamental driving equations of this material. I want to introduce thermodynamics to you. Just the fundamental principles, so you sort of see the landscape that we're going to head over the next few lessons. We've seen that energy transforms from one state to another, but we've never talked about in which direction. Why does it happen in that direction? Why can't we naturally go up a hill like we naturally go down a hill? And talking about spontaneous or reversible processes. So, the resulting changes in forms of energy must follow conservation of energy, and we are going to focus on these quantities. Internal energy, which we talked about before, and in specific, the component of internal energy, thermal energy that's measured by temperature heat. We're going to look at heat, which is energy in transit. We're going to look at work, which is energy in transit. And pressure and volume, those are also state functions. Interestingly enough, the first law of thermodynamics is the zeroth law. And to be honest, I forget about the zeroth law, not so much because we don't usually start counting with zero. If you're in computer land, you probably do. But the zeroth law, because it's sort of one of those blasé, obvious laws. It's the definition of thermal equilibrium. And I'm just going to introduce it here so I don't have to do another lesson on it. Thermal equilibrium is two systems can freely exchange heat with no net flow from one to the other. So that's thermal equilibrium. There's energy moving about, right? All of the molecules in those substances are moving about, but there's no net from one to the other. And inherent by thermal equilibrium, we're going to assume that there's one temperature throughout that whole substance of those two objects in contact with one another. So that's the definition. If you need to reference it, come back to this point in the slide, and so I won't have to do a lesson on it later. The next law is, of course, the first law, and it really talks about energy and how it's conserved in all thermal processes. We're going to break it down into different components and study those components and how that affects the system, and get used to terminology. This is a point where the terminology gets kind of specific with terms that you may use every day. The zeroth law talks about what thermal equilibrium is. The second law talks about if it's not in thermal equilibrium, what is the direction of energy movement? And so this is a fundamental principle. So this is the rule for energy transfer. The direction of energy transfer in spontaneous processes is from hot to cold. The systems, this is another corollary of the second law. Systems tend and progress to the greatest disorder at thermal and chemical equilibrium. So you can see that there's a couple of caveats on this law, and it's gets a whole lesson to itself, and I will explain this later. But we look at energy transfer, and then this is also a point in time where we start thinking about entropy. And so I will give a lesson on entropy and disorder, why it always tends towards disorder. And we're looking at not only thermal equilibrium, but also chemical equilibrium. So if you're a chemist, if you're studying chemistry, this is the point where you study thermal theory with chemistry. Kinetic theory with chemistry is how does the heat being added or the process being endo or exothermic affect the process of that reaction, and how fast, and what it requires, what is required in order to facilitate that reaction in chemistry. With thermal, we just have a natural flow. The third law says absolute zero is not attainable, and I'm going to hold on to this thought because I'm going to talk about it more in a second here. I will say this overall is that when considered, these are the fundamental principles, laws of thermodynamics. Everything that is studied stems from these laws. I wanted to highlight the structure of the thermodynamics unit as we move into it, again, so that you can have a feel for the landscape and be able to anticipate how different concepts fit together with one another. I'm going to study the first law first, where we talk about energy conservation and get into particulars about internal energy, or delta U, and the gain or loss of heat and work. Okay, so we're keeping heat and work separate in this situation. So we're going to look at an equation in there, and we're going to look at work done by gases. I know that's really interesting that gas does work, but we'll look into that and study the ideal gas law with all the thermal processes in there. So applications of the first law is the thermal processes. Then we'll study the second law, which is rules for energy flow and changes in entropy. We'll look at applications of that, which is engines and heat pumps, and get a simple model going for you about how we can extract work from a cold reservoir and a hot reservoir, and think of that in terms of energy flow and also entropy. So I'm going to cover entropy in there and speak broadly about the concept because it's a fascinating and relevant concept, and introduce a few equations, nothing major, so that you have a grounding in there. I've already talked about the zeroth law of thermal equilibrium on the prior slide, and I'm actually going to take a moment right now in order to talk about the third law, which is the law regarding absolute zero. So here's the third law of thermodynamics. The third law is, I like to think of it in two components. What it is not is a system cannot be brought to absolute zero through no finite number of processes. So this is a very technical definition. For me, in like the bigger picture, it means there's always motion. That's what the third law says. We cannot have zero motion. Absolute zero, right? If we're looking at temperature, 1/2 mv squared equals 3/2 kT if we're looking at a single molecule. And this is the average speed over a whole container. So temperature is related to the motion. There's always motion, so there will always be temperature. So there's no absolute zero is able to happen at all. There's no way we can extract all of the energy out of a system. That's also what it says. There will always be a temperature. There will always be some sort of motion or vibration anywhere. What it is, I like this definition because it talks about entropy, and we saw that on the previous slide. With thermodynamics, we talk about energy, but then we start getting into entropy. And so entropy talks about disorder, and that's where this definition comes from, is what it is, the entropy of a perfect crystal. And when you think about a perfect crystal, that's when everything is lined up perfectly. There's so much order. Like a diamond, when all the carbon atoms get lined up into a very precise geometry, a perfect crystal at absolute zero is exactly equal to zero. So the entropy, when there's no temperature and all of those molecules, atoms, whatever they are perfectly lined up. They're not vibrating. They're not translating. They're not rotating. There's no disorder. The entropy is equal to zero. And so that's not a possible situation, right? There is always disorder. There will always be disorder as much as there will always be a temperature and always be motion. So that's what the third law encapsulates. I don't have any problems to quantify for that, but it may come up as a concept so you're aware that these things are true. And that's the end of this lecture.